around that mRNA. I want you to think of it as my finger is mRNA and my hand is just going to kind of wrap around the mRNA. And that's kind of what happens. All right, that's going to allow the rRNA to read it. Okay? So the blue thing that I just drew around the mRNA is rRNA. That's its job. It's to read the code. It's to read the codons. It's to announce it to the tRNA, which reside within the cytoplasm as well. So we're going to draw tRNAs now. We're going to draw them with little chicken feet. Those are tRNAs. They too are made up of nucleotides. So they too are going to have nitrogen bases. And there are going to be very specific tRNAs. And so, GAU is our first codon. So there exists within the cytoplasm a complement to that. Tell me what the complement to GAU would be on this tRNA, this first one right here. What should this first one be right here? The nucleotide should have what nitrogen base on it? If this is a G, this has to be C. The next one would be U, and then the last one, based on U being a nitrogen base on the mRNA, that would be at A. See that? Tell me what the next tRNA would be based on CUG. So this would be G, next one would be A, the next one would be C. All right? Those have a special name as well. Those are complementing the codon. Those are, for lack of a better name, called anticodons. Now I told you that the tRNA is responsible for constructing the protein, putting amino acids together. So they're going to be carrying amino acids. So let's put amino acids on the tRNA. That's an amino acid. That's an amino acid. And they're going to be different amino acids. Why? Because the anticodon is different. The anticodon is specific for a specific amino acid. So I'll draw them there. I'll put stripes in this one and I'll put little dots in that one. But both of those are amino acids. The red thing, I should say things because there's two of them. The red thing is tRNA. All right? And we'll just point at the little circles there. Those are amino acids being carried. Where are they carrying them to? They're carrying them to the messenger RNA. That's their destination. That's, in essence, what translation is. So we can put a third arrow here. These two guys, or gals, things, are going to literally, like a spaceship, dock. Again, the bases, the pairing, fit together like two pieces of a puzzle. So, this C right here is going to connect beautifully with this G. And this A right here, or this U I should say right there, is going to pair beautifully with that A. And the A is going to pair beautifully with the U. And it just sits right there. And it interconnects. And so now we have amino acids sitting right here. And then the next tRNA right next to it docks. Now these two amino acids are right next to each other. What are they going to do? They're going to be bound to each other. What have we just produced? What kind of structure have we just produced? It starts with a P.
Protein.
It is protein structure, but specific. There's 4 types of protein structure. What are we producing here? We're putting the amino acids in a sequence. Primary structure. What we're doing here, by lining up these amino acids next to each other, based on the anticodons of the tRNA, which are based on the codons of the mRNA, which are based on the gene of a DNA molecule, the original recipe, is to stick amino acids next to each other so that we can, at some point, do that. So we talked initially about primary structure of a protein. That's how it's done. And the amino acids are put in the correct sequence. Why? Because the tRNAs are bringing the right amino acids with them because their anticodon needs to dock with the codon. Why is the codon the right codon? Because the gene was the right gene. That's why. We just made a protein. So what's number 3? What's that line, those 2 lines that I just drew? That's translation. So number 3. 2 is just the mRNA leaving the nucleus and going into the cytoplasm. Number 3, we're just going to call it translation. That's the noun. We're translating mRNA. When we do that, we make primary structure. And then there's secondary structure. And then there's tertiary structure. We've just constructed a globular protein. That's how it's done. Regardless of what protein is in your body, that's what had to happen in order for it to be there. Every protein in your body is produced, and that's how cells do it. They do it by transcribing a gene and then translating the mRNA that was produced by transcription. And we get primary sequence, or primary structure, I should say. Are we good? Now to make it even more clear, or if it's not clear yet, hopefully this helps clear it up. 2 animations. They've been on pilot now for a week and a half. And I'm going to show them to you now. So both of these are already on pilot. And there's 2 of them. The first one's transcription, and the second one's translation. So we have a 2-stranded molecule here. What do you think that is? That's DNA. All right? And so we're going to see some extra stuff in this animation. I don't care that you know it. All I care is that you understand that we have a gene within the DNA molecule, and then we're going to transcribe it, and we're going to see how that happens. They're going to mention they're going to mention the enzyme. I don't care. They're going to mention hairpin loops. They're going to mention 3' and 5'. I don't care. All right? All I care about is what we've done. Complementary base pairing. I want you to know how to do that. I want you to know where transcription happens in the nucleus. I want you to know what's being produced in mRNA. I want you to know what's being transcribed, a gene. I want you to know that the gene is a recipe for a protein. That's it. Okay? So let's look at the animation.
The synthesis of messenger RNA is called transcription.
That's the enzyme.
Transcription begins.
Promoter region. I don't care. What do you think that purple thing is? That's coming out of the butt of the green thing.
Ribosome?
Not the ribosome. What are we making? mRNA.
The telophase strand of
So that's the mRNA being constructed by that enzyme based on the gene. All right, so now what they're about to show is the actual gene. So there's our gene right there. That's on the DNA, right? That's the DNA strand. So given that gene right there, CTGAC, what's going to be the complement to that? What's going to be the what are going to be the nitrogen bases based on that? It's going to be G, A, C, U, beautiful, not T, right? Because we're making RNA. It will be U, and then that should be a G.
the complementary single-stranded messenger RNA molecule.
Bam. All right? And it's the enzyme pulling together the nucleotides with these specific nitrogen bases. It's putting it in the perfect order. That is assuming that the gene is correct. Sometimes genes get screwed up. And we'll talk about what that is and the consequences of that in just a second. All right? So, that's pretty much all I need you to know when it comes to this part of the animation. Okay? We've just produced mRNA. And it's produced from scratch, de novo, from new. Okay? It's not floating around. We make it all the time. It needs to be made all the time. These enzymes here are busy. You're constantly making proteins. You never, ever, ever, ever stop. All right? So now we have this particular strand of mRNA. It's in the nucleus. It's going to go into the cytoplasm now. Now we move on to translation. So this is the mRNA molecule. There is the recipe right there. That's the copy, I should say. What do you think this is? It's the tRNA. What do you think the circle is? That is a specific amino acid called thymine. You don't have to know that. Okay, there's 20 different amino acids, as I said before, although you don't have to know that. But that tRNA is carrying a very specific amino acid based on UAC. Tell me again what UAC is. What would we call UAC? We would call that the anticodon. Again, anticodon tRNA. End of story. AUG, does that complement UAC? Yeah. A complements U, U complements A, G complements C. We have our first tRNA that's going to land right there. By the way, AUG is called what? That's a codon, right? 3 nitrogen bases in sequence on an mRNA molecule is a codon. And then we have CCG, codon, UAC, codon, GAU, codon. We need to read it first though. This doesn't know what to do or where to go unless it's told. So what do you think that is? That's the rRNA, the purple thing. And we're going to see it wrap around the mRNA. All right? So here we go.
In prokaryotic cells, translation.
Okay, blah, blah, blah. So,
TR.
that's the rRNA. That's the blue dotted thing that I drew around my mRNA. That purple glob there, that's this. That's this thing. And it's going to read the code. It's going to read the codons in sequence. Very good, it works. We assume that it does. Let's see what happens.
RNA and messenger RNA. The 50S ribosomal subunit then joins the complex.
I don't care about 50S right now, I don't care. rRNA, that's all I care about. Okay? And what it does, what its job is.
Proteins called.
Did you notice it just docked, like a ship? All right, like 2 pieces of a puzzle. All right, I should say 3 pieces of a puzzle. Okay, because there's 3 nitrogen bases in an anticodon and a codon. They just fit like 2 pieces of a puzzle. Okay, this cannot dock right there. Can't. It would not fit. It would not work. It just doesn't go there. We need another tRNA to come down with the different amino acid. How do we know the amino acid is going to be different? Because the anticodon is going to be different. How do we know the anticodon is going to be different? Because the codon is different than that one.
Initiation factors are also involved, but are not shown.
I don't care.
The 70S ribosome has 2 sites to which transfer RNA carrying amino acids
I don't
combine.
care, I don't care, I don't care, I don't care. Now I
The
care.
amino acid then moves into the A site. The formal methionine carried by the transfer RNA in the P site is then joined to the amino acid carried by the transfer RNA.
And it just keeps going. And it just keeps going. Another tRNA with another amino acid. tRNA with amino acid, tRNA, amino acid. What have we done here? We're stringing together amino acids. We are creating primary structure. And the amino acids that are strung together in just the perfect order. Why? Because these tRNAs, based on the anticodon, are going to bring a specific amino acid to a specific codon, and we assume the codons are correct because we assume the gene is correct. So if a gene has the right sequence, if a gene has the right nucleotides in sequence, then the mRNA is going to have the right nucleotides in sequence, which means the tRNA is going to carry the right amino acid to the right spot. They're going to be put together in just the right sequence, and we're going to have a protein that gets put together perfectly and works perfectly. And most often, that's exactly what happens, although sometimes it doesn't. And we'll talk about what that is in just a second. All right? So by the time it's all said and done, we have a protein.
Elongation of the polypeptide is terminated when a stop codon
I
moves.
don't care. All right, I don't care about A site, P site, I don't care about any of it. I don't care about the stop codon, the start codon, I don't care. I want you to know what we've discussed. How is a protein made? This is how protein's made. That's how protein's made. Okay? When you watch these animations, one of the good things that you can do to help yourself turn the sound off, you narrate it. That's one of the ways to use these animations. You be the narrator. All right? And certainly you want to draw this from script. Do you want to draw that and just stare at it? Well, you might want to do that because it's less work. But if you want to truly learn it, then you might have to draw that a dozen times from scratch until you can do it without hesitating one time. As I said in that big long email, isn't that what I said? You know the information when you can go from start to finish without one bit of hesitation, saying it out loud, not in your head, because if you say it in your head, you'll just gloss over things. It happens. I've been there. Okay? It's been a long time since I've been in college, but I still remember. All right? Are we good? Yes? Big picture is what? How to make a protein. Okay? What time do we have? Let's take a break. 2 minutes. And by the way, we have a little announcement during the break, so as you're kind of paying